us Vassu comes to us from Stony Brook University, and he's going to tell us about from photons to parity, high precision tracking across two distinct frontiers of nuclear physics. And I guess those two frontiers include heavy ions and
Jacak.
Very good.
Okay.
The floor is yours.
Thank you. Thank you for the introduction, and it's an absolute pleasure to be here. As Barbara mentioned, I will be talking about the tracking developments that we applied across two very different scenarios, from precision electron scattering to probe physics beyond the standard model with the upcoming MOLLER experiment at Jefferson Lab, to complex heavy ion collisions to study the properties of partonic matter with the PHENIX experiment at Brook. So I'll start with the PHENIX analysis, where we tried to study the heavy flavor pair production through the dilepton continuum channel in PP collisions at 200 G. Okay. The plot on the right shows a schematic dilepton invariant mass spectrum. On the horizontal axis is the invariant mass of the lepton pair, and on the vertical axis is the yield in arbitrary units. The red line is the sum of all the known contributions. We have the pi 0 eta and omega Dalits in the very low mass region, and then there are the vector meson contributions coming from rho, omega, phi, j psi, and psi prime. The region of interest in this invariant mass spectrum is the intermediate mass region between the phi and the j psi, where a significant contribution is expected to come from thermal emission from the QGP. Now, other than a small Drellian contribution, the main physics background in this region originates from the semi-leptonic decays of open heavy flavor mesons, the D and the B hadrons. Now, these heavy flavor hadrons have relatively long lifetimes, causing their decay electrons to originate many microns away from the interaction vertex. And with a vertex detector, we can measure these displaced vertices pretty precisely and disentangle the thermal component from the semi-leptonic component, and that's where the vertex detector comes into play. A lot of people in this room are familiar with that, I think. Now, before...
I thought Star also has the heavy flavor tracker for that purpose, right?
Yes. And before we can actually do the disentanglement between the thermal component and the semi-leptonic component, it's really important that we have a good understanding of the heavy flavor contribution itself, and that's where the BP system comes into play. Now, PHENIX installed a vertex tracker back in 2011, and that was the primary motivation for installing it, to study heavy flavor production. But there's a caveat here. The vertex detector in PHENIX comes along with a huge photon conversion background. And that is the largest challenge for this analysis that we are trying to do here. On the left is a beam view of the PHENIX detector setup. The detectors relevant for this analysis are the vertex detector over here, which is also shown in the exploded view. There are 4 layers in total. For tracking, we have the drift chambers and the pad chambers, and electron identification comes from a combination of information from the rich detector and the EMCAD. Now, one thing to note here is that the radial extent of the vertex detector is only of the order of like 20 centimeters, give or take. But the drift chamber, which is the tracking detector, that sits at around 220 centimeters away from the interaction vertex, and it's only this much. So we have like a 20 centimeter track segment over here in space, and tracking through all that space in between is actually pretty challenging over here, unlike the DTC, where you have a lot of space points along the trajectory. Now, as I mentioned, the vertex detector with a nearly 15% radiation length gives off a lot of photon conversions, and as such, most of the electron tracks in a sample are conversion tracks, and it becomes really important for us to come up with some kind of a technique or an algorithm to suppress this background before we can see anything meaningful in the mass spectrum. Now, imagine for a second that I am proposing this strategy that whatever drift chamber track I want to keep in my sample must have a corresponding hit in the innermost VDX layer. That should ideally remove any conversions originating from the outer VDX layers, and that's where most of the material budget is anyway setting. But for this kind of an approach to work, the first and the foremost thing that we have to make sure is that the matching between the drift chamber tracks and their right hits in the vertex detector is reliable, because if that's not the case, it's not going to work, right? So let me tell you, it was far from reliable. There were a number of issues that we had to account for before we could even think about suppressing this background. One of the largest issues was a distorted event vertex information from the vertex detector. And that was there because there was pileup in the vertex detector. In run 15, the beam luminosities were very, very high, and that combined with a relatively longer integration time of the vertex detector resulted in the VTX capturing data from multiple events for each recorded event. And you can imagine that this would clearly distort the event vertex information. Now, as a byproduct, if the event vertex information is not reliable, the corresponding match that you would want to get between the drift chamber tracks and the hits in the vertex detector is not going to be reliable. So the byproduct of that. But that was actually not the only problem over here. There were also geometrical misalignments between the two detector subsystems. And last but not the least, the behavior of the pixel and the strip pixel layers, the vertex detector on the whole, was not replicated in a proper way in the simulation framework, which is very important when you're trying to do a DCA technique to disentangle the components. Okay, so let me show you two events from real events where you can see that the drift chamber tracks are matched to the right hits in the vertex detector pretty nicely, which are highlighted by the red rectangles over here. This is after we implemented all the corrections and calibrations to account for all the issues that I just mentioned. Now, in the following few slides, I'll tell you a little bit in more detail about the issues and how did we fix for those. Okay. As I mentioned, the vertex information coming from the vertex detector was not reliable, and that affected a huge fraction of the events. And quantitatively, for more than 90% of the events, the vertex reconstruction was not done properly. Now, we did come up with an independent way to calculate or determine the Z vertex ourselves, using the VTX hits corresponding to those tracks that were simultaneously measured by the drift chamber and the EMCAL, the details of which I'll not be going into. But once that technique was implemented in data, that led to a nearly 10 times increase in pair statistics, which is a remarkable achievement because we were able to get hold of the lost data, because this analysis is statistics only.
Question? So you said this is for proton-proton collision?
Yes.
So this sounds surprising, 90% events. So if you notice a event, you have some sort of, trigger requirement that says there's a physical event here.
Yes.
So very low multiplicity, maybe you miss it, but 90%, this seems, why is such a large fraction of vertex is not properly reconstructed?
Because the detector was taking up data from multiple events, but it was only recording one event, but
it's a pileup.
It was a pileup issue.
Screwing everything up, okay.
Because luminosities were only increased to such high values after run 14, and we are doing the run 15 analysis.
And you didn't have a fast detector that could do vertexing?
No, not at the
That's
time.
the reason, okay.
No. The integration time was pretty long. And the resolution that we got, yes.
Can you just tell me, is a vertex where the hadron becomes photons exactly? Like, is that what you mean by vertex?
The vertex is where the event happened. So in a bunch crossing, imagine if a PP collision is happening. So wherever the collision is happening, that's what the event vertex means.
Okay. So may I ask, what is your event trigger?
Oh, it's the minimum bias trigger, and we are using the ERD trigger with a coincidence with the minimum bias trigger.
What was the minimum bias? Forward oscillators?
The BPCs.
They don't have enough timing to tell.
The multiplicity is pretty low, so the resolution that you will get with I'll come to that. I'll come to that. Yeah. So this is why I have written this statement, exactly because what you're asking. The resolution that we get for the vertex determination with this new technique that we implemented was of the order of 0.8 3 centimeters, and I want you to remember this number because it's pretty important. I'll come back to it later. Now, of course, before we implemented this technique in data, we did look at its validity in the Monte Carlo world, because of course you will do that. The two plots shown here are residual distributions between the reconstructed z-vertex and the true z-vertex along the horizontal axis, plotted as a function of the PT of the track. In single pion simulations on the left, which is a proxy for the primary tracks directly coming out of the vertex itself. And when we use the conversion E plus E minus tracks in single photon simulations on the right, which is an extreme to the primary tracks that we are using on the left-hand side. And you can see that in both these plots, the z-vertex resolution that we are getting is similar. And that is also evident in the plot over here, which is the residual distribution in the 1 to 2 GeV bin for both the photons and the pion simulations, which also gives off a z-vertex resolution of the order of 0.3 centimeters, which is what we found in the data as well. So that is a good thing that our simulation and data are agreeing with each other. Now coming to the geometrical misalignments part that I talked about. If we want to have a reliable match between the drift chamber tracks and the hits in the vertex detector, you can't avoid that. You have to have a good understanding of the relative alignment of the two detector subsystems. And we have taken zero field data in order to identify any such issues if there are. And the two plots shown here are the mean of the delta phi distribution along the vertical axis, plotted as a function of the azimuthal angle of the track itself in both the drift chamber arms, the east and the west arm. Now, delta phi here is defined as the phi of the drift chamber track and the phi of the VTX hits in some initial search window, because that will tell you if there are any misalignments between the two or not, if you combine the information of the two detectors. Now you can see from both these plots that there are actually some major misalignments between the two detector subsystems. But okay, we found the issue and we can correct for that using this functional form over here that we have used to fit the data. And these were the two major issues that we dealt with, the vertex reconstruction not being proper and the geometrical misalignments between the detector subsystems. But now the thing is, we can actually improve on our track hit matching further. That's because the drift chamber tracking algorithm that we have, that makes assumption that whatever track there is, it comes from the interaction vertex, because the tracking through all that space in between is pretty hard and you need to have some initial condition on that as well when you're traversing the track through the magnetic field. And now that interaction vertex is assumed to be 0, 0 and BBCZ. Now BBCZ is the Z vertex that we have determined from the beam counters on both sides of the interaction vertex, and it's similar to the V0 detectors in ALICE. Very loosely, I'm not exactly sure, but I think it is similar to the V0 detectors. Now, coming back to your question, we could have used the BBC's determined Z vertex for our analysis. But the track multiplicity in PP is so low that the resolution that we get with the BBC for the Z vertex determination is of the order of 3 centimeters. And I just showed you that we can do 10 times better if we implement the Z vertex determination by ourselves. That number was 0.3 centimeters. And that is clearly one avenue where you can improve the tracking itself, that can further improve the matching between the drift chamber tracks and the hits in the vertex detector. Now, I'm talking about 20-year-old boards, okay? So before you start messing with these, it's really important that you have a good estimate of the magnitude of these corrections. So that's what I'm going to give you here. Let me talk about the azimuthal angle phi 0 of the track first. And if you're trying to make a correction in the phi 0 on account of a more precise vertex information, you will need the Vx and the Vy values, right? Now in PP collisions, the track multiplicities are again pretty low. So the vertex resolution that we have in the transverse direction is limited by the beam spot size. And we don't really have any means to reconstruct that ourselves like we did for the VC component. Now these Vx and Vy values are typically of the order of less than half a centimeter. And now I'm asking the question as to I have a track segment at 220 centimeters in space. And if I want to join that segment with the 0, 0 coordinate, or I want to join that segment with the 0.5, 0.5 coordinate. It's not going to make any difference whatsoever. But the picture can change quite a lot when you talk about the polar angle of the track, the theta 0 of the track. Now in the z direction, there is not much track bending, and that allows us to calculate the form of the correction analytically on account of the more precise z vertex information from the vertex detector. The formula for the correction I have included over here, and delta z in this equation is the difference between the BBC determined z vertex and the VTX determined z vertex. And it's evident from this plot of delta z over here that it can be as large as a few centimeters. And so to sum up, maybe it's not that relevant for phi, but for theta, it actually can be pretty relevant when we replace the BBC information with the VTX information. And in the next slide, I'll show you how much. The two plots shown here are the delta theta distribution along the vertical axis, plotted as a function of the polar angle of the track, theta 0, similarly to how I did it for the phi direction. Delta theta is again the theta of the track minus the theta of the VTX hits in some initial search window. On the left-hand side is when I use the BBC determined z vertex, and on the right-hand side is when we use the z vertex that we determined with our technique. And you can see the massive improvement in the spread in going from left to right. And I actually want to emphasize the scale here. It's in radians. So when you're using the BBC determined z vertex, your spread is actually of the order of 80 to 90 millirad, just quite a lot. But when I use the VTX z vertex, we were able to reduce that resolution by at least a factor of 4 or so. So it was actually a massive improvement in the tracking itself. So now let me show you how do all these corrections that I have talked about until now, how our results are shaped by that. We started from a distribution that looks here, the delta phi plotted as a function of the PT of the track at the outermost VTX layer when there were no corrections or calibrations applied. And you can see that the distribution is pretty skewed, right? But once those corrections and calibrations have been implemented, we end up with the plot in the middle, which is a lot more as to what you would have expected and with a better resolution. And the corresponding resolution for delta phi is plotted here as a function of the PT of the track or for all 4 VTX layers. Now you might be wondering about the shape of this curve. In the low PT region, you have 2 factors that are competing with each other. You have the multiple scattering effect, and then you have the beam spot resolution itself. But when you go to the high PT part, it's mostly the beam spot resolution that's playing its role, and multiple scattering becomes a little insignificant, and that's why you get this kind of a shape over here. Okay, so now the thing is that we were able to remove these problems that we had with the vertex detector, and now the next part is that, okay, you have to now come up with some kind of a matching algorithm between the drift chamber tracks and the corresponding hits in the vertex detector. And with this improved resolution, we can actually do that with quite a high efficiency. Now, if you ask the question as to how would one do that, you would take a drift chamber track, you would swim it through the magnetic field and project it onto the layers of the vertex detector. And now you start looking for hits around those projections in some search window, right? That's the basic algorithm that we took. And now the only question is, how do we define the size of those search windows? In what window do we have to look for? We cannot go just like large and take every hit that lies in that window. And that's exactly where the resolution for delta phi and delta theta plays its role. That's where these plots come in handy to define the size of those search windows. And that's basically what I have defined over here. How did we achieve our track hit association? And now you can ask me the question as to, it's possible that in that search window you have more than one hit line, and most of the cases that's what happened. And in such cases, we assign that hit to the track for which the function delta d defined over here is a minimum. You can think of it as some sigmalized distance in the theta phi space. And that's how we achieved our track hit association. I want to mention that these things existed in the vertex detector, but we started with just the hits information and did the matching and everything ourselves. Okay. Next, we can quantify the efficiency of these vertex layers. And by that, I mean the probability of finding a hit on a given vertex layer for a given drift chamber track. You can imagine that this efficiency is nothing but a reflection of the dead regions in the detector. And the efficiency here is plotted as a function of the PD of the track using hadron tracks in data, which are shown by the solid circles, and in single pion simulations shown by the open circles at all 4 layers of the vertex detector. And there is a pretty good agreement between the data and the simulation. The simulation is, of course, tuned to the data. Now, what I want you to take away from this plot is that the vertex detector is actually pretty dead. The most efficient is actually the innermost layer with nearly an 84% efficiency, and then the outer 3 layers are sitting at 60%, which is quite a lot dead when you're trying to do a pair analysis with a 2-arm geometry.
Why is it so dead?
Bites me.
That wasn't your problem, huh? You just
So we found out that the detector was behaving in a very peculiar way during the runs, where during half of the run, the electronics was functioning properly, and the other half of the runs, it wasn't. So it was like an on and off behavior, which is...
So it was intermittent, or did half the run,
It was intermittent.
so they're interspersed?
Yes, so within the same run, it was functioning some of the times and not functioning half of the times.
How do you detect that? How do you?
Let me, okay, I'm gonna go to the slide probably because I
know
want
when you realize, but then it just.
No, I wanna show you that.
I'd like to see it too.
I wanna show you, okay, I got very far away.
Okay. Yeah.
Wow.
So it so happened that I was not looking at a Cole-Z plot. I was looking at just the projection, and that's where we found the issue, that it was actually dead during some part of the run. And
So what are these plots? Each one is a run?
yes, it is one
So if
run.
it's gray, then part of the run was dead?
Yeah. As surprised as you are, yes.
Oh.
Which one was this?
Run 15.
So that was the first.
No, the vertex detector was installed in 2011. So
Okay,
it was,
so that, okay.
so that is one part of the reason where it was behaving weirdly.
I think there's a hand.
Yeah, Ernst has his hand up. Go ahead, Ernst.
Yeah, thanks for sharing this. And again, also not to
What?
distract from what you really want to talk about, of course. But is this understood in terms of the true underlying cause, or put differently, do you know for fact, let's say, that this is uncorrelated with, for example, beam intensity or luminosity?
If I have to take a guess, I think it was just the electronics. But why it did not happen in run 14, or maybe it did happen, I haven't looked at run 14 myself. Maybe it was the case there as well. So I won't be able to give a concrete answer to your question.
Okay, thank you. Again, not meant to distract.
No, of course not. So let me quickly jump back.
So you did use these partially functioning runs?
Yeah.
So and you had to do
It's
that?
again, it's statistics hungry.
You had no
cannot-
choice.
No.
Okay.
No.
You're a very brave man.
Okay, so there I was. So the takeaway from this slide was the vertex detector is pretty dead. Okay. So now that we have obtained a reliable track hit matching, we can go back and look at the efficiency of the approach that I introduced in the first slide, as to we can ask for every drift chamber track to have a hit in the innermost VTX layer, and that should remove the conversions from the outer VTX layers. Now I'm going to show you what the efficiency of the conversion rejection with that technique is. The plot here shows the rejection probability plotted as a function of the PD of the track in single photon simulations. And you can see that with just the innermost hit requirement, we are removing nearly 98% of the conversion tracks on a track by track basis, which is quite a high efficiency. But we'll see how does that correspond to when we look at the mass spectrum, because maybe the percentage is high, but the absolute number is still pretty large that the combinatorial just blows up. So that is yet to be seen. Now with the vertex detector, you can actually further improve your conversion rejection probability. You can take advantage of the fact that the conversion tracks are two inherently nearby tracks. Now the drift chamber sits all the way behind the magnetic field and just have a two-arm geometry, 90 degree on one side and 90 degree on the other side. And it often only reconstructs one of the conversion tracks, but the vertex detector on the other hand is exposed to much less field in detail. And the tracks in the vertex detector also don't get bent that much, which means that you can look for those neighboring hits for that known reconstructed drift chamber track. And consequently, if a track does have such a nearby hit in some narrow window of size delta phi cross delta z, which we call as the veto windows after the conversion veto algorithm name, we can tag that as a conversion track and just throw it out of a sample. So we are just making use of the geometry here, that the tracks will not be bent that much in the vertex detector, and even if it's not reconstructed in the drift chamber, the hits will still be there. So let me show you the final performance of our conversion rejection techniques. The plot over here is the rejection probability as a function of the PD of the track using single photon simulations in 3 different veto window sizes. This is the rejection probability for those tracks that survived the innermost hit requirement. So with the largest window size, the leftover conversion tracks are being rejected to nearly 86% efficiency. So it's quite a lot of conversion rejection that we're trying to do here. But of course, it's possible that in the process, you will also lose some of the primary tracks. And we can quantify that using the hadron tracks in data. And that's what the plot shows here, the rejection probability as a function of the PD of the track using the hadron tracks in data. Now, this is the rejection probability with the combined effect of the innermost hit requirement and the conversion veto looking for the neighboring hit. And you see that with the largest window size, you're only removing nearly 4% of the primary tracks, which is not dramatic compared to the conversion rejection that we have. Now, before I move on to the mass spectrum itself, there is actually one more improvement that we can make in the resolution with which the phi 0, the azimuthal angle of the track, is determined. So we are basically trying to change the entire tracking.
A question on your last one. So a few slides ago, I thought you said the efficiency of the innermost layer was 86%. How do you get a rejection? Then how do you get a rejection probability higher than the 86%?
Because we are using the combined information from all the 4 layers. If we find a hit in any of the 4 layers, because in PP we can do that, in gold we can't.
Okay.
Of course, in gold, the rate is lower too.
Yeah, So the phi 0 resolution, we can improve that as well. So we are basically changing the entire tracking in PHENIX. The 2 plots shown here are again the residual distributions between the true phi 0 of the track and the reconstructed phi 0 of the track along the horizontal axis, plotted as a function of the PD of the track. On the left-hand side is when I use the default phi 0 reconstructed by the drift chamber, whatever the tracking algorithm is giving me, versus when we reconstruct the phi 0 ourselves. Now, how do we do that? We use the VTX hits assigned to the track itself. So it's like a 2-level process. You assign the hits first, and then you use the assigned hits to further determine what the phi 0 is going to be. And you can see the massive improvement in going from left to right in the resolution. And as such, at the lowest PD, we were able to improve this resolution by a factor of nearly 4.
Can we think of that as a refit? First you do your pattern recognition.
It is exactly that. Yes. And why is this resolution important? Because it's directly going to translate to a better mass resolution, because phi 0 is what defines the opening angle of the pair. So now, the golden plot, the mass spectrum itself. On the left-hand side, I have the invariant mass of the E plus E minus pair as a function of the yield within the PHENIX acceptance. The black points are when we didn't have any track hit association or any conversion rejection whatsoever. But once we applied all those things, we ended up with the red points over here, where you can see the typical features of the spectrum pretty clearly. So the conversion rejection was definitely working. And on the right-hand side, I'm also including the combinatorial mixed event background on top the idea behind that is that the combinatorial background is actually getting reduced to a level where we can see the spectrum. Moving forward to the measurements in the DCA space, which is what the vertex detector is for. We calculate a transverse DCA of the drift chamber tracks to the interaction vertex using the equation shown over here, L minus R, where R is the radius of trajectory of the circular track and L is the distance between the center of that circle to the interaction vertex determined by the VDX. And I hope this picture clears out how this calculation is done. It's important that we know what the resolution for the transverse DCA determination is, because that's what the input to the simulation is going to be. The plot on the left shows the transverse DCA resolution distribution plotted as a function of the PT of the track using the hadron tracks in data. And the corresponding resolution is plotted here as a function of the PT for data points in red and for single pion simulations in black. And the two are again in pretty good agreement with each other. And the shape of the curve is again because of the two competing factors in the low PT region, which is the multiple scattering plus the beam spot resolution. But in the high PT, it's mostly the beam spot resolution that plays its role. So good that we do understand the resolution for a DC transverse determination. Now using the single track DCA, we can define a pair DCA.
Oh, good, thank you. Yeah, I didn't see it. It was hidden behind. Zhenyu, go ahead, please.
Sorry, can you hear me? So I have a question on the previous slide. So you said simulation is tuned to data. So what kind of tuning did you do?
In the simulation, we don't have the beam spot spread put in. So that is one major thing that we put in the simulation to tune. And then there are the efficiency maps as well, because I showed you the on-off behavior of the pixel and the strip pixel layers. That also needs to be put into the simulation so it can better match the data. So these were the two major things that were done to tune the simulation.
So you just basically did a smearing for the beam spot resolution.
Smearing for the beam spot and efficiency maps for the detector.
Okay, got it.
Using the single track DCA, we defined a pair DCA using this equation over here. And the plot on top shows the average of the pair transverse DCA along the vertical axis, plotted as a function of the invariant mass of the E plus E minus pair. The takeaway from this plot is that you can see that this distribution exhibits a minimum around the Jefferson mass region. And that is actually the largest contribution there will be in that mass region. We will see that in the following slides as well. And that is the prompt contribution. So you would expect the DCA to be very small over there. But as you move to the smaller mass region, you add on more and more semi-electronic component, and that would make your average go larger. And that's what we see in this plot as well. Now let me show you how do the measured foreground pairs compare to the cocktail of hadronic decays. I have included here the vector meson contributions and the Dalitz contributions, and the Drellian contribution is simulated using the Pythia 8 framework. There are a lot of curves over here, you don't have to worry about that. The only thing to note here is the sum of all these contributions in the solid, pink or violet, whatever you want to call it, that line. Okay. What I have not included here is the background and the heavy flavor contribution, and I'll come to that. But let me focus onto the Jefferson region for a second. You can see that even with the missing components, the cocktail is right over there, especially in the Jefferson mass bin, and that can only mean one thing, that the contribution of those missing components has to be really small in that mass region.
See, I'm worried about the normal, I'm just looking at vertical axis.
Yeah.
About the normalization, how's the cocktail normalized? How are they both normalized?
They're independently normalized, and that's the power of this technique. So after doing the Z deconstruction ourselves, when we did the event normalization, and the JPSI and the other components were normalized according to the previous measurements in PHENIX. They are not normalized with respect to the
cocktail.
Yeah.
So it's an absolute normalization.
Yes. Yes. And it was not possible until we did the Z vertex reconstruction ourselves, because we were losing a lot of the desired events. And yeah. Interesting. So now let me come to the goal. of this talk, obtaining the heavy flavor continuum in the intermediate mass region. And the only thing stopping you from getting that is the background. You need to know what the background is in the intermediate mass region so that you can get the heavy flavor continuum. How do we obtain the background? The plot over here shows the invariant mass spectrum in the PHENIX acceptance. The red points are the combinatorial mixed event background that I already showed you before. But from the point of view of obtaining the heavy flavor continuum, it's kind of useless because it doesn't have any correlated background in it. Now, in the past and up until now, I should say, people have used the like sign foreground, and by that I mean the E plus E plus and the E minus pairs from within the same event, corrected that for the relative acceptance differences between the like and the unlike sign, and that was used until now as a proxy for the background under the pair continuum, and that is shown by the black points over here. Now the problem with this approximation is, first of all, it's an approximation. Why? Because it just does not contain the correlated and the combinatorial background. It also has a signal component in it, and that comes from the bottom decays. Now, bottom can give off like sign pairs through these two mechanisms. One is the famous P0 B0 bar mixing, the oscillation behavior. And the other one is the B can give off an electron and a D meson, and the D can further give off an electron of the same sign nature. And that is the reason we didn't want to use this approximation in our analysis, because we have the vertex detector. Because with the vertex detector, we don't really have to rely on this approximation, and we can determine the background ourselves. That's where the true power of the vertex detector lies. In various mass bands of this invariant mass spectrum, we use this technique called the DCA template fitting. And in each of these mass bands, we fitted the DC of the measured foreground pairs with 4 different templates. So the colors are not really coming out nicely. I'm sorry about that. The black points are the foreground measured pairs. And in this mass region, which is right above the phi, which is relatively a lower mass region, you can see that the major contribution is actually given by the background over here. I'm just going to point it out because the colors are not that good. And then the prompt and the CC bar contributions are sitting over here. But now the picture changes quite a lot when you move to the Jefferson mass region, because now the background is actually sitting all the way down over there, and the measure point is over there. And the major contribution is actually given by the prompt and the CC bar components, which proves our hypothesis in the previous slide that I mentioned, that the background contribution has to be really, really small, especially in the Jefferson mass region, and the DCA gave that out, which is, yes.
I'm going to suggest something. I may have the geometry totally screwed up, so you'll tell me.
Mm-hmm.
But it seems that the physical forget it. I'll tell you after. I was thinking about negative DCAs, combinatorial. So let me just tell you what I was thinking about, and I'm pausing because I have totally screwed it up. Combinatorial can have either sign DCA, whereas physical decays have positive DCA.
Yeah.
Is that relevant here?
No.
Yeah, that's what
Because the definition doesn't allow for a negative DCA.
You do a template fit to the DCA
Yes.
distribution, then yes.
Yes. Okay. So now we use this DCA template fitting technique in order to get the background experimentally without relying on any approximation from the like sign foreground. But because we are limited in statistics, we employed a sliding window technique. And by that, I mean overlapping mass bands for the DCA template fitting. And the effect of that overlap is then eventually taken into account in the final background determination. And the background that we obtain from that technique is shown by the red points over here in the mass spectrum on the left plot, which I'm showing above the phi. And the corresponding acceptance corrected like sign foreground, which has been used until now as the proxy for the background, is shown by the green points over here. And you can see that there is clearly a deviation between the two, especially in the high mass region, which is kind of good because in the high mass region is where you would expect the bottom contribution to be dominant. And that's where you would expect the shapes to go different. Now that you have all the relevant components in the intermediate mass region, obtaining the heavy flavor continuum is pretty straightforward. And the result is shown by the black points in the plot on the right. And we have also compared this to a Pythia simulation of heavy flavor and Relian, the sum of which is shown by the dotted black curve. And within the accuracy of our measurement, the two seem to be in pretty good agreement with each other. Now that we have the heavy flavor continuum with us, the next step that we want to do is to experimentally disentangle the charm and the bottom contributions using the same DCA technique that we have developed for determining the background. And that is something on our plate, and we are currently in the process of doing that. And eventually, we would also want to compare these extracted charm and bottom contributions to theoretical models, because we want to assess the role of MPIs in heavy flavor production at RIC energies. That is something unexplored at PHENIX, at least. And these are the two major key points that will be the highlight in our publication out of it, which is under progress. Okay, so if there are any quick questions until now,
I do have a question about the theoretical predictions. So, are there already theoretical predictions, and what will you learn by checking them?
So we have done that until now with Pythia 8, because now they have that MPI framework where you can switch it off and on. And what we have found with respect to the charm production is that the cross section does change by nearly a factor of 2 when you switch that on or off, not for the bottom, for the charm. Now, from the previous PHENIX measurements from the heavy flavor single electron analysis, the NLO predictions were always short by a factor of nearly 1 point something, nearly 2. And we will something in that lens, hoping that that might be the issue, and that's why we are looking at the role of MPIs through the heavy flavor continuum.
Cool. And I guess nobody else has done that yet.
No.
Very nice. I guess we haven't done that explicitly in Alice either, have we?
The measuring is the feedback cross section and BB bar from the lepton.
Yeah. The cross section, yes, but the question of the MPI contribution.
But we can explore in a different way, so I think it's not really necessary for us to use this.
We can, but we haven't yet, right?
But
or have we?
I don't think it's. Maybe I'm wrong, but what we do, I don't know, as a function of multiplicity and so on, the self-normalized yield is already doing well. So I don't think we have to measure in this way. I don't see any gain actually, because anyway, this analysis is Vassu explained, quite complicated.
No, I'm not arguing we should do the analysis the same way. My question was just, do we know at LHC energy how important the MPIs are?
Oh yeah, the role of the MPI was quite intensively explored by the self-normalized yield of the deimagined JSI.
And is it a factor too?
It has to be more than that, right? Because MPIs in Alice, LHC energies are a lot more relevant than at RIC energies.
Yeah, then also what we do is usually compare the one with the p-step curve basically with and without MPI on.
Yeah.
So actually, I think nobody really quantified the mean number of the, but because
but we have observed that it's significant. Not put a number to it.
Yeah, exactly.
So when Vassu puts a number to it, he'll be the first.
But I don't know, because actually it's really hard to quantify indeed. I think.
In data.
Okay. So you have your challenge laid out.
But here, I think in the previous slide, here, it's basically what you do is relying on the Pythia to extract each contribution. Then what would be the uncertainty for?
This is just a comparison that I'm showing. We will extract the charm and the bottom ourselves using the DCA. That's the next goal. Right now, this is just a comparison that I'm showing you.
But okay.
This is not the final picture.
The data is the sum, right?
Yes. It's not the final picture.
But in the end, the template should be driven from the Monte Carlo, or?
So he won't need a template, right?
Yeah.
I'll let him go into MOLLER.
Okay. We can obviously continue this discussion.
Yeah.
I just have one more part to go. Okay. Now I will switch gears and talk about the tracking development in a completely different electron scattering environment for this upcoming MOLLER experiment at Jefferson Lab. For this experiment, we were primarily responsible for coming up with the strategies and the techniques to carry out the kinematics measurement. But let me give you a little bit of background on the experiment itself. The MOLLER experiment is aiming to measure this parity violating asymmetry APV defined over here. Sigma R and sigma L are the polarization dependent cross sections. And this asymmetry will be measured in the scattering of longitudinally polarized electrons of unpolarized electrons in liquid hydrogen target using the upgraded 11 GeV beam at Hall A in Jefferson Lab. It's a pretty long sentence, I'm sorry about that. APV in molar scattering is proportional to the weak charge of the electron, which in turn is proportional to the weak mixing angle, which is a fundamental parameter of the standard electroweak theory. The goal of the experiment is to precisely measure this parity violating asymmetry APV so that we have an overall fractional accuracy of nearly 2.3% in the weak charge measurement. That's a very, very high precision goal. And that would make it the first low Q-square experiment to measure this quantity to such a high precision. And that's what makes this pretty important and special. Here's a layout of the experimental design. We have the liquid hydrogen target over here, which is actually pretty long. It's 125 centimeters long. And then we have the acceptance defining collimator, which has a 7-fold symmetry. That is followed by the combination of the upstream and the downstream toroidal magnets, which is in a way the heart of the experiment because it provides enough kinematic separation between the signal and the background. The signal being the EE scattering and the background being the EP scattering in the liquid hydrogen target. Down there, we have a bunch of detectors, the tracking detectors and the main integrating detector where the APV measurement will be carried out, and some other detectors as well. And eventually there is the beam dump. So this is basically the layout of the experiment. The entire hole is around like 30 meters. The experiment from here to here is around 30 meters long. So let me focus onto the kinematics measurement itself, which was my main contribution to this experiment. There are mainly two goals of this kinematics measurement, but I think those are actually two of the most important. There are others as well. The first one is to verify the acceptance of our toroidal spectrometer system. And the second is to determine the average kinematic factor and the uncertainty associated with it. And that is the part I'll be mainly focusing on. Now, this kinematic factor is nothing else but the parity violating asymmetry divided by the weak charge of the electron. And whatever's left in this equation, you can look at the terms and it's purely spectrometer and target dependent. So whatever the final predictions will be of the experiment, this is very important in defining or guiding the final eventual uncertainty in the measurement. And that's why it's actually pretty important. And the goal is to measure the kinematic factor to a fractional accuracy of less than 0.5%, which is again a very high precision goal. And that is important if we want to achieve the desired accuracy in the weak charge measurement. And in order to make this measurement, we need the tracking information on the scattered electrons. And that's where the tracking detectors come into play, which are sitting right upstream of the main integrating detector over here. So let me pause here for a second and discuss what the strategy is going to be for determining this average kinematic factor. From this equation, you can see that there are two factors that we have to worry about. One is the incident electron energy E beam, and the second is the scattered electron energy E prime. Simple. Incident, scattered. And for molar scattered electrons, because it's the EE scattering, it's very well studied. There is a 1-to-1 correlation between the scattering angle theta and the scattered electron energy E prime. So what it means is that once you have a handle on the scattering angle theta, you know what E prime is, you know what your scattered electron, what your incident electron energy is, and voila, you have the kinematic factor. But lives are not simple. Because of our long liquid hydrogen target, it's 125 centimeters long. Both the incident and the scattered electrons undergo radiation losses within the target, and we really need to take that into account if we want to achieve the final accuracy in our measurement. And I'll come back to this. Focusing a little bit on the tracking detectors, we will have 4 layers of gas electron multipliers. And in each of these layers, we will have 7 GEM modules. That amounts to a total of 28, and half of those were actually built in Stony Brook. These tracking detectors will be mounted on a pair of rotating wheels so that we can ideally make the measurement in the entire azimuth. And from these tracking detectors, we will have the information on the radial and the azimuthal location of the track, r and phi, as well as their directions r prime and phi prime. So these are the total 4 gem variables that we will have from the tracking detectors. And the goal is to obtain some kind of a map between the gem information and the scattered electron information, out of which I'll mostly focus on the scattering angle theta. That's what's important for our strategy. Another equipment that we need is a sieve slit collimator, which, as the name suggests, it's a collimator with a bunch of strategically placed holes in it. And the idea behind using such a collimator is to pick out tracks with a particular theta and phi. And in a giant force simulation framework, this is where the sieve sits. The sieve is here, and the acceptance defining collimator is over here. And it sits before the magnetic elements, and the gem is right over there. So it's important to have an understanding of where these elements sit with respect to each other. And as for the target, we will be using thin carbon foils. And with the simulation studies, we found out that 3 would be enough. The upstream, downstream, and the midstream, the naming convention. And we will measure the, make the measurement at 4 lower beam energies, 2.2, 4.4, 6.6, and 8.8. So it's like a beam energy scan that we have to do.
Can I ask a question about this sieve?
Yes.
Is its purpose just for calibration or do you?
Yes.
Okay.
It's just calibration. Okay. Yes. It's actually this kinematics measurement, the other name for it is optics calibration. Yeah. Okay. Yeah. Now, designing the sieve was actually a very crucial part of this endeavor, and we spent an enormous amount of time. Let me stress it out.
Colander.
There were a lot of constraints that we had to take into account while designing it. For example, what the hole diameter should be, what the orientation of the holes should be, should they be running parallel to the beam axis or there should be some tilt to them, what should be the radial and the phi location of the holes, should be all those sorts of constraints. The final realization of the physical sieve, the picture is shown over here, and this is right now sitting in the lab. This is actually the final sieve that we designed. So before I move on to the reconstruction algorithm, let me show you a couple distributions of the scattered electrons once they pass through the sieve and reach the first gem plane over here. On the left is a gem R versus gem phi distribution, and on the right is a gem R prime versus phi distribution. And you can see the sieve hole patterns pretty clearly. And you can also see some of the scattered radiative events over here, all over, scattered over there. So let me now come to the reconstruction algorithm itself. Let me remind you the idea was to obtain from the gem information R prime, phi prime, the information on the scattering angle theta. We perform an initial cleanup of the data to remove those radiative events. And once that is done, we combine the data from all the carbon foils and all 4 beam energies that I mentioned before, and perform a simultaneous fit of the scattering angle theta in terms of gem R and R prime. And the result of that fit is shown in this plot over here. It's actually a simultaneous 3D fit, but I'm showing you the projections over here.
Why do you need the 4 beam energies?
I'll come to that. The scattering angle theta here is plotted as a function of gem R. And in this plot, it's plotted as a function of gem R prime. You can see the 4 beam energies structure over here. The blue points are the true values, the Monte Carlo values, and the orange points are the corresponding predictions. And the residual distribution for the scattering angle determination is shown in this plot over here. And the resolution that you get for the scattering angle determination is of the order of 0.6 millirad. But this number doesn't really mean anything right now because we don't know how much is it going to translate to the kinematic factor determination, and we will see that. But now the good news is we do have a way to reconstruct the scattering angle theta. And now we have to use that information to reconstruct the scattering angle for the molar scattered electrons. And the corresponding residual distribution is shown over here for the molar scattered electrons. And the resolution that you get is of the order of 0.7 millirad, which is a little worse than what we had with the carbon-12 data, but it's not that dramatic. But good news is now I have a handle on the scattering angle theta. I can use this relation, the one-to-one relation between theta and E prime, to predict what the scattered electron energy is going to be. But now I'll come back to the question as to we need to account for the radiation losses that happen within the target. Now think about it, you have a long liquid hydrogen target, an electron is incident and it traverses some distance inside the target before it performs an interaction. Now modeling the energy loss that it had to go through while traversing that distance is simply the Becker-Bloch formula, it's DEDS, right? And all you need to know is how much distance it has traversed. Or in other words, you need to know where the electron originated from within the target, the VZ. And we don't have a vertex detector over here. And actually, predicting VZ is pretty straightforward because we can make use of the fact that there is no magnetic field between the target and the sieve. And once I have a scattering angle theta prediction, I can use the radius of the sieve hole the track went through and use the simple trigonometric relation over here to predict where the electron came from within the target. Simple geometry, pretty straightforward. And let me show you how the VZ residuals look like for the molar scattered electrons. The resolution is of the order of 23 centimeters for a 125 centimeters long target. So I wouldn't say it's like very good, but it cannot be better because we are using the sieve hole center for any track that passed through that sieve hole. So there is a spread right over there. But once you have a VZ prediction, modeling the energy losses in the incident and the scattered electrons is not that difficult. And I have included some information in the slides over here, but I'll not go through the details of that. It's just modeling. Yeah.
Very nice question about liquid hydrogen targets. Can you actually vary the density? In other words, you'll vary the effective length or the amount of Bremsstrahlung?
No, because it will be a liquid hydrogen target. Because we need the liquid form to get the interaction rate to get the final statistical accuracy. But once you have the beam on the target, it will change the density locally over there. So those are different effects.
You change the length of it.
I think if you have a more than 125, it's going to be very difficult.
Less.
I think it's, I had the same question, but I think the answer to that is you need to have the interaction rate that much.
So it's some idealized sweet spot. Maybe it's just what they have.
I'm going to go with that.
Okay.
So here is the final result from here. The kinematic factor plotted as a function of the scattering angle theta. On the left is the true Monte Carlo information, nothing. But on the right is when we use the reconstructive variables. We reconstructed the scattering angle. We use that to predict what the scattered electron energy E prime is going to be, modeled the energy losses into that, and then finally reconstructed the kinematic factor. Now, if you compare the average values of these kinematic factors between the two, you will see that we could actually reconstruct the kinematic factor to a fractional accuracy of less than 0.2%, which is less than the 0.5% requirement. But it should be taken with a grain of salt because it's not the final ultimate uncertainty. But as far as the reconstruction is concerned, we are fine. There will be some other factors at play, but we would only know that once the experiment runs. So this is like a yet to be seen thing. And all of this is important so that MOLLER can very precisely measure the weak mixing angle far more accurately than any of the other low energy measurements that you can see in this plot over here. There is this Q-weak experiment that Jacak performed with the EP scattering, then the E158, the pioneering experiment at SLAC, and then there's the atomic parity violation experiment, all of those much bigger uncertainties. And MOLLER is trying to achieve a very, very high uncertainty, and the kinematic factor determination is a direct ingredient in that. And with the data taking expected to be starting in 2 years from now, we can hope some good results out of it, and it's going to be pretty exciting. And that brings me to my summary. I talked about the dilepton continuum measurements with PHENIX, where we improved an already existing tracking algorithm to a level where we can suppress the background and achieve the heavy flavor continuum in an almost model independent way without relying on any approximations. And then I talked about the kinematic measurements for MOLLER, where we didn't only come up with the strategies and the techniques, but also developed the tracking algorithm and reconstructed the kinematic factor to a fractional accuracy of less than what was desired. So thank you for listening, and any questions are welcome.
So we already asked a lot of questions, but are there any additional ones?
I want to answer the question that you asked.
Okay.
Okay. So the curve that I'm showing here is the scattered electron energy E prime as a function of the scattering angle theta. Now for the molar scattered electrons, it's an identical EE scattering, so you get this kind of like a band over here. But when you're using the carbon-12 atoms over there, it's an EC12 scattering, which is much more massive than the electron. So the scattered electron has this monotonic scattered electron energy. And that's why we need to perform the beam energy scan so that we can cover the full thing over there.
Yeah, I kind of saw that from the plot, the fact that
Yes.
the different energies with the different lines. Thanks. Sorry for the dumb question. Tucker.
Yeah.
With the misalignment that you were talking about on slide 10, was that misalignment like a remaining misalignment after like a preliminary alignment that had already been done, or is it's like an additional step alignment, there was no alignment done and it had that,
No. So whenever the repairs are done on the detectors, for example, they are taken out and they're put back in. It's customary to take the zero field data after that to account for those issues. So those calibrations are not done automatically for us. We have to do this.
Okay, so you did the
How do you handle this inefficiency, what you showed during the run due to the electronics?
We make some efficiency maps for that. So there are
but you cannot do
800
run, but
no
run by run or
run by run. There were 844 runs for which those efficiency maps were made and then applied to the simulation.
Okay.
Yeah.
So you basically make the efficiency map from the data.
Yes.
Well, we also have efficiency maps run by run for some stuff now.
Yeah, but we have a much smaller run list than 800.
It was more like an unfortunate thing that happened. I mean, detective working for half the run and half for not, it's like very unusual. It just happened, okay, we had to deal with it, fine.
But you couldn't really figure out any correlation between the beam operation and the
No, because I haven't looked at the other runs, so I cannot comment on that. That's the thing.
You just calibrated it out.
For run 15, yeah.
Do you know if these intermittent inefficiencies were correlated in different regions of the detector?
No. So these were ladder by ladder connections.
You know that they were not?
Yeah.
Otherwise, that would affect your pair acceptance.
Yes.
So you verified that?
Yeah, that much we did. If within the same run, if there are any efficiency issues, we looked at that. But within, like, okay, when I say run 14 and run 15, like that, like different years, that we didn't know. The gold code analysis is going on right now, and we actually have some reasonable looking dial-up-tone spectrum out of it, because in gold code, the multiplicities are like way too large than in PPP. So the combinatorial becomes squared times high. And with these rejection techniques, I don't have that slide right now, but we have a reasonably looking dial-up-tone spectrum in the 20 to 40. 0 to 20 is still quite a lot, combinatorial left, but yeah.
Well, let's thank Vassu again.
I think very impressive.
Thank you.